Great. Thank you for all being on time. Welcome to this second revision webinar in our series for 2019. This is for GCSE Chemistry students on the subject of atomic structure and the periodic table. So I'm going to start by going into some of the teaching around this topic, but this is really, to use an Americanism, this is kind of Chemistry 101. This is the most fundamental ideas, some of the most fundamental ideas in chemistry, and some of the ideas in this topic underlie your teaching and understanding and learning about chemistry all the way through the rest of your chemistry course. So in a way, in some ways, the ideas in this topic are so fundamental and so important that it's very, very important to get those down and understood very, very well. So in that vein, I want to start by focusing on a few words. Chemistry is for many students challenging because it's a kind of unhappy no man's land somewhere between physics and biology, in the sense that, like biology, there's a lot to remember, and like physics, there's a lot of problem solving. But unlike physics, not all of the principles in chemistry are immediate. You can't immediately arrive at all of these principles from first principles by logical deduction. There's a lot that you have to learn, and there's a lot of lateral thinking involved. So some of these ideas are so fundamental that it's really important to not mess up your understanding of chemistry by getting them right first time. So chemistry is fundamentally the science of the understanding of the properties of matter. So matter is physical stuff, and you might have heard it referred to as such. That's a pretty good definition for matter. I mean, we could get more technical, but that's okay. As far as GCSE sciences is concerned, matter is simply physical stuff. So solids, liquids, gases, and lots of other states of matter that you don't really go into a great deal in GCSE sciences. But this is what matter is. Now, this matter is obviously very, very diverse. So if you look in the room around you, you're probably going to spot several thousand, or maybe even tens of thousands, if not hundreds of thousands, of different types of materials or matter. You're going to find metallic materials. You're going to find alloys, which are mixtures of metallic materials. You're going to find plastics, which are polymers. You're going to find solids, liquids, gases, all kinds of different elements and compounds. And so matter is so diverse that if you're a chemist and it's your business to understand the properties of matter, one of the things that you need to be able to do immediately is to be able to categorize matter. And the way that matter is categorized in chemistry is like this. Generally speaking, matter can be categorized as pure substances. Now, I'm going to put the term pure in brackets here because, strictly speaking, it's not really necessary. The term substances in chemistry has a very specific definition, which we'll see in a moment. Now, these pure substances are pure in the sense that the only other categorization of matter is in terms of mixtures of different pure substances. So the other types of matter are mixtures, and I'll put in brackets of pure substances. So you have either pure substances, materials which are categorized as pure substances, or you have materials which are categorized as impure substances or mixtures of different pure substances. So I'll give you an example here. If you look around the room, you might find something which is made of wood or some other biological material like, I don't know, cotton or something like that. Now, biological materials like wood are incredibly complex, essentially mixtures of many, many, many different compounds, which in themselves, those compounds are pure substances. So, and similarly, the atmosphere, the air in the atmosphere is a mixture of many different elements and compounds. And so you have mixtures of elements and compounds are the two types of pure substance. So a pure substance is either an element or a compound. So this is the fundamental categorization of matter, but this is where we're going to start because, as we'll see, chemistry is fundamentally the science of understanding the physical and the chemical properties of matter. But like physics and like biology, when we try to understand something on the macroscopic scale, in other words, the physical properties of a liquid, usually what we end up doing is explaining why those properties are the way that they are in terms of things on the microscopic or the submicroscopic scale. So in the case of chemistry, it's all about particles and also the bonding between those particles. And the next topic that we're going to get into in chemistry is in fact about the structure and the bonding within materials. But before we get into that, we need to cover these fundamental ideas first. So matter, all physical stuff, basically, is what we mean by matter. Pure substances are either elements or compounds. So I'm going to use a slightly different color here to illustrate the next point. Let's just pick a nice green here. Okay, so the other thing about pure substances versus mixtures of pure substances is that pure substances can be described in terms of having a unique chemical formula. Pure substances, elements, compounds, they have unique chemical formulae, expressions that describe the composition of those substances in terms of which atoms those substances are made of. Now, I've used a very important key term there, atoms. Now, the term atom is what we're going to get into in a moment, but as we'll see, the term element is defined in terms of the word atoms. So an element is usually defined in GCSE terms, at least, as a pure substance. I'm just going to use the word substance here because the word substance is very specific here. A substance composed of atoms, each of which has the same number of protons. So in other words, what we're saying here really is the same atomic number. Now, if we examine this definition a little bit more closely, what we'll see is that the term element then is being defined in terms of another key term, atoms. And the term element also requires not just atoms, but atoms which are identical to each other in the sense that they have the same number of protons. Now, as we'll see, this is also this idea of atoms and number of protons is not just fundamental to the word element, it's also fundamental to another term that we're going to be looking at, the term isotope. So this is what an element is. It's a pure substance composed of atoms, each of which has the same number of protons or the same atomic number. Now, elements don't necessarily have to be made of individual unbonded atoms. Elements can have chemical formulae, like, for example, so examples here of elements would be things like hydrogen. Now, hydrogen, the symbol H on the periodic table on its own. So let's take a look at our periodic table here. So the symbol for the element hydrogen is H, but this is just a symbol which describes the unique atoms which compose that element, that substance. So the substance hydrogen is made up of only hydrogen atoms, which only have the atomic number 1. Now, in this periodic table, you may be a little bit confused to see that the atomic numbers are displayed in the top left-hand corner, and the relative atomic masses are displayed in the bottom left-hand corner. Now, don't let this confuse you, because some periodic tables will display them the other way around. But the way that you can always tell is atomic numbers are always integers. They are always whole numbers. And furthermore, the atomic number of each element increases by 1 as you go across each horizontal row of the periodic table, called the periods of the periodic table. Now, we're going to get into the structure of the periodic table a little bit later on, but we're going to be using this periodic table here because it's quite useful and quite interactive. And I'd recommend you guys use this one yourself. This URL is very, very useful for a number of reasons. So hydrogen, only the element hydrogen has the atomic number 1. Only atoms of hydrogen have 1 proton in their nuclei. So hydrogen, the symbol for an atom of hydrogen is H. However, hydrogen atoms in ordinary conditions, in standard conditions, they don't exist as separate atoms. They bond with each other and they form pairs of hydrogen atoms in molecules. So here we have the formula, the chemical formula for molecular hydrogen. And we see here that only hydrogen has this molecular formula. So elements are pure substances because each element has a unique chemical formula, in the same way that, for example, other types of elements that we're going to be looking at, for example, chlorine, Cl is the symbol for one atom of chlorine. It's also the symbol on the periodic table for the element chlorine. But when you write Cl in a chemical equation, if you just write Cl on its own, what you're describing is a single atom of chlorine. Now, like hydrogen, atoms of chlorine don't exist in isolation under standard conditions. In fact, they bond with each other to form diatomic molecules. So we have this term atom, but there's this other term over here that we need to define as well. The term molecule also has to be defined. So we've already used the word atom. We also need to make sure that we're confident that we can define the term molecule as well. So we'll come back to those in a moment. So those are elements, but what about compounds then? Well, compounds are formally defined as pure substances. They are pure substances, so we can start our definition with that. So compounds are pure substances. Now, it's a pure substance. Each compound has a unique chemical formula, but they must be dissimilar to elements, and they are. These are pure substances composed of atoms of different elements. And these are chemically bonded together. So that's what a compound is. So, for example, we can take atoms of hydrogen, atoms of chlorine, and chemically bond them together into atoms of HCl, hydrogen chloride. So this would be an example of a compound. Again, hydrogen chloride is the only compound that has this unique chemical formula. And because of that, this compound is in fact a pure substance. So pure substances composed of atoms of different elements chemically bonded together like hydrogen chloride. Another common example would be water, H2O. So here we have atoms of different elements, hydrogen and oxygen, which are chemically bonded together. So there's an incredibly important term here as well, chemical bonding, which we need to get into shortly as well. So we have here another really, really important concept, the idea that elements and compounds are both pure substances. But you see here that, again, we're using this term atom. The term atom is fundamental. So now that we've gotten to this point, we now need to give ourselves a definition of the term mixture. Now, the mixture can simply be, it's a very simple, in some ways, a simple definition, but you really, to understand the term mixture, we need to understand a little bit more about the distinction between chemical bonding and another kind of bonding called physical bonding. So, what we see here are elements. These are the purest substances that you can have because they're composed of only one type of atom. Some elements are monatomic. So the elements in group 0, sometimes called group 8, or the noble gases, the elements in this column here are monatomic elements because, as we'll see, the atoms of these elements do not bond easily with the atoms of other elements, and so they exist as separate atoms. But these elements are in the minority in the periodic table. Generally speaking, the atoms of other elements typically will combine or chemically bond with atoms of either the same element or other elements. But you do have monatomic elements, so we can give one of these as an example. So argon is an example. Xenon is another example. Now, these elements do not generally bond with other atoms of other elements, but under extreme conditions, they can be induced to form bonds. So you can make, for example, a compound of xenon with fluorine called xenon tetrafluoride, which has the formula XeF4, xenon tetra meaning 4, fluoride. So again, this is a compound. So let's have a look. Before we get into the definition of mixtures here, we need to add a definition to our growing list of definitions to really make sure that we fully understand this topic here. So we have the term atom, we have the term molecule, we have the term chemical bonding, but there's also the term physical bonding, which is another kind of bonding. Now, I'm not going to get into too much about chemical and physical bonding in this topic beyond just some of the basics, because in fact, the next GCSE chemistry topic will be all about chemical and physical bonding. And so we're going to get into that in a lot more depth later on. But for the moment, let's see if we can define these terms and clarify exactly the kinds of, make sure that we're clear on these words, because one of the reasons it's so important to memorize definitions, formal definitions, is not just because you may be asked what each term is or to define each term. It's also because it's very important that you're able to use these terms appropriately in your explanatory and descriptive answers in exams, particularly those questions which require longer written answers, like the 6-mark questions and the 4-mark questions, which are ranked in terms of level 0, level 1, and level 2 answers. So let's now define for ourselves what we mean by these terms here. So let's start with atom here. Now, if an element is a substance composed of atoms, each of which has the same number of protons, then an atom can also be defined in terms of the word element. Now, the word atom actually comes from an ancient Greek concept of the indivisible particle, or the atomos. Now, we're going to get into the development of the atomic model actually next. But for the moment, the word atom literally means the smallest particle of matter into which any element can be divided, which still has the chemical properties of that element. So an atom is the smallest particle of an element which retains the chemical properties of that element. Okay, so that's what an atom is. But you see here that the definition of the word atom is contingent on you being able to understand what we mean by an element. It's also contingent on you understanding what we mean by chemical properties. So what about molecule then? Well, atoms can chemically bond with each other to form larger particles called molecules. So a molecule, now the word molecule can be defined in various different contexts in chemistry slightly differently. We're going to stick to a fairly broad definition here. The term molecule is a particle, so it's a small piece of matter, a particle composed of more than one atom. So it can be 2 atoms, it can be 3, it can be any number of atoms, but it's still a particle. It's a very small piece of matter. It's a particle made up of more than one atom. And here's the key point. These atoms must be chemically bonded together. So here again, we have a definition of a term which requires you to understand and use another key term and yet another key term. So this covers many of the most important and fundamental definitions in chemistry. Now, these last 2 remaining ones, I'm going to define first by telling you what the similarity between these 2 is. So both of these terms use the term bonding. These are both types of bonding. So before we define each of these, it's worthwhile noting what is a bond. So a bond in chemistry, the term bond means this is an electrostatic force of attraction. So this is a force between particles. So essentially, a bond, whether you're talking about a chemical bond or a physical bond, the thing that they share in common is chemical bonding and physical bonding. These are all examples of electrostatic forces of attraction, forces which attract particles together due to the attractions between positives and negatives. Now, the way in which these different types of bonding work and their strengths are radically different, but they do share this in common. bonds in general in chemistry, whether you're talking about physical or chemical bonds, and physical bonds are sometimes called intermolecular forces. All of these are electrostatic forces. They're not gravitational forces, they're not magnetic forces, they're not nuclear forces. They are forces which cause particles to be attracted to each other due to attractions between positives and negatives. So in that case, if they share this aspect, then what is the difference? Well, chemical bonding is electrostatic forces, again, of attraction, and these are between atoms or ions. Now, this is what a chemical bond is. It's an electrostatic force of attraction between particles, but those particles are atoms or ions. So here we see that there is a distinction between at least 3 different kinds of particles that we've named. Atoms are particles, molecules are particles, ions are also particles. And so we need to define the word particle as well and distinguish between them, because these are words that you'll see used on pretty much every page of every chemistry textbook everywhere. So what is physical bonding then? Well, again, physical bonding is bonding, and so we can start by defining it as an electrostatic forces of attraction. But this time, it is between particles, but those particles are molecules. So physical bonding are electrostatic forces of attraction between molecules. And so there is a difference. I'm going to use a slightly different color here to make this point. The strength of chemical bonds is much, much greater than the strength of physical bonds. Much stronger. So chemical bonds are much stronger than physical bonds. Another thing that we need to make a point about is the following. Rapidly running out of interesting colors here, perhaps not. Let's pick purple. Right, so here's another important point about bonding. Chemical bonding. So the chemical bonding that exists in a material. So in other words, the type of chemical bonding, the strength of chemical bonding, etc. in a material. Now again, I'm using the word material here because that it refers to the chemical bonding within elements and compounds, pure substances, but also the chemical bonding within the elements and or compounds that make up a mixture. The chemical bonding in a material determines the chemical properties of that material. So, in fact, let me rub this out and make a bit more space. We'll define the term particle in a moment. So the chemical bonding, the type, the strength of chemical bonding that you find in an element, in a compound, or in the components of a mixture, this is what determines the chemical properties of those materials. Now, in contrast, the type of the physical bonding, so again, the type, the strength of physical bonding, etc., and the structure, the arrangement of particles, as we'll see in the next topic, in a material, this is what determines the physical properties. This is why they're called chemical bonding and physical bonding. Physical properties. So this what we've talked about so far gives you an overview of the most fundamental concepts. Matter is fundamentally made up of particles. Made up of smaller pieces of matter called particles. Now those particles, as we've seen, these can be atoms, they can be molecules, or they can be ions. And ions are basically atoms or molecules which have a net positive or negative charge. Atoms, if something is defined as an atom, it has an even number of positive and negative charges in it, protons and electrons, and therefore is electrically neutral. But if an atom loses or gains electrons, it becomes an ion. Similarly, molecules typically are uncharged or neutral overall, but if they gain or lose electrons, they can become positively or negatively charged. So this is the most fundamental series of terms and their definitions in chemistry. You really must make sure that you understand not just what these terms mean, but also how they are related to each other. And the fundamental point is this, and we're going to get into this in the next topic: the type of chemical bonding that exists in a material and the structure, the arrangement of particles with those chemical bonds between them in a material, this determines the chemical properties. Now, by chemical properties, what we mean basically is reactivity. So the word chemical properties means reactivity. How do they react? How vigorously do they react? What do they react with? Reactivity. Physical properties, on the other hand, are things that can be measured using physical means. So things like boiling points, melting points. In other words, properties which can be measured physically, measured or observed in physical processes. So this now brings us back finally to the definition of a mixture. A mixture is a combination of pure substances, either elements and or compounds. So I'm probably going to need a bit more space for this one, but I'll just write it down here. So the term mixture, this is defined as a physical combination. So in other words, what we're doing is we're not chemically combining, we're not doing a chemical reaction between the components of that mixture, the elements and the compounds, we are physically combining them, a physical combination of different elements or different pure substances, elements or compounds. Now the implication here is that mixtures of pure elements and pure substances, elements and compounds, if you're producing that mixture using a physical process, for example, you take sand, silicon dioxide mainly in one bucket and salt, sodium chloride in another bucket, you put them together in a larger single bucket and you put a big stick in it and you mix it about. You're physically combining those substances because there's no chemical reaction taking place between the sand and the salt. And the implication is the physical process that you did to combine those two substances to make your mixture can be reversed using a physical series of processes. In this case, in this example, you would maybe, for example, pour some water into the bucket, dissolve the salt in the water, and dissolving is an example of a physical process. And then you then filter the salt solution from that bucket containing the sand in the salt solution. So the sand is left behind on the filter. The filtrate becomes the salt solution, and then you evaporate the salt solution. But all of those processes are physical processes. None of them involve chemical reactions. So producing the mixture was simply mixing physically those two granular solids together in a big bucket. Separating those substances required you to dissolve and then filter and then evaporate. All three of those are physical processes. So when you make a physical combination of different pure substances, there are no chemical changes taking place because the chemical formula of a substance, so let's define this one up here. The chemical formula of a substance is an expression of the unique ratio of atoms of each element in that substance. So when you mix sodium chloride, salt, with water, H2O, you have still H2O molecules and sodium and chloride ions. They're floating around in solution, but you haven't changed the chemical formulae of anything. You have mixed them together using a physical process. And similarly, you can separate them out again. You can evaporate the water and you still have H2O molecules. They just happen to be in the gas state. And you then have solid sodium chloride left behind. So this is basically, probably the most important set of definitions that you can possibly learn in chemistry. And these are definitions that will come up not just in this topic, but in every other topic that you will learn about in chemistry. I see a lot of pins dropping in the chat. Seems like a lot of you haven't had these explained properly. Great, so I'm glad that this is helping. Excellent. Okay, so now that we've laid the groundwork by defining these very, very important terms for ourselves, and I would encourage you again, always, always, always memorize your definitions, and also just have a go at sketching out the connections between different definitions and how one definition feeds into another one, because this will help you to better formulate your language when you're describing and explaining in exam questions, and get more marks, and also perhaps just as importantly, avoid losing marks by using these terms incorrectly. Okay, so now that we've laid the groundwork, let's get into this topic. So I'm going to be going through the teaching of this topic roughly in the order in which you guys voted for the topics to be covered. Again, anything that we don't have time to cover, I will be placing the slides for this entire PowerPoint, all of them, onto the private webinar resources page for you. So please do continue to ask questions. I will respond to you there. Right, so I mentioned that the atomic model, our understanding of the atom, it starts with the ancient Greeks. In fact, arguably it starts earlier than that with various other ancient cultures, but in the Western academic tradition, for some reason, people focus starting on the ancient Greeks. So I'm just going to stick with that here, because that's what your exam boards stick with. None of them talk about the atomists among the ancient Indians or anything like that. So we're going to start there. So the ancient Greeks, they were talking about matter. They were looking at physical stuff around them, and they were just having a kind of philosophical discussion. Some of their philosophers, one side of this discussion was philosophers who believed that if you took a piece of matter, let's just say you take a piece of wood, you divide it down the middle, and you end up with two pieces of wood. Well, that group of philosophers said that, well, you could then take one of those halves and then divide that in half. You get a quarter. You take that quarter, you divide that in half, you get an eighth, and so on. You keep dividing each one of those smaller and smaller fragments. And their argument was that, in principle, you could continue to divide forever, getting smaller and smaller and smaller and smaller pieces of matter, and there would be no limit to how small the matter could be divided. Another group of philosophers argued that that's not the case, that sooner or later you would get to a piece of matter that was so small that it was indivisible, that it was the fundamental unit, the smallest possible unit of matter. And this was called the atomos. Tomos in ancient Greek means to divide or to cut or to split. Atomos means the indivisible or the uncuttable one. And so the term atomos was used to describe the indivisible or the uncuttable particle. And so the ancient Greeks, led by a philosopher named Democritus, the atomists, the people who thought that you couldn't divide beyond this smallest fundamental unit, eventually came to, I guess, win the argument, in the sense that their idea was promulgated into the kind of mainstream. So that was the ancient conception, but they didn't really think beyond that. And again, the ancient Greeks were, the arguments that they were having were philosophical in nature. They were based upon logic and argument, but there was very little in the way of actual experimentation of the kind of scientific investigation that we know of now. But the first person in the Western tradition to really move forward the ideas of the ancient Greeks was John Dalton, this gentleman here. So in 1806, the chemical elements were defined by Dalton as being pure substances composed of only one type of atom. And so again, this is really where we get this definition here from. It was actually Dalton's definition, fundamentally. So he also introduced the idea that atoms were simply featureless solid balls, that they didn't have any internal structure at all, that they were just a featureless ball of matter, and that they had no internal structure. We now define an element as a substance composed of atoms, each of which has the same number of protons, but this is based upon John Dalton's definition of the word atom. And again, that in turn is based upon the work of the ancient Greeks. Now, the next person to take forward our understanding of the term atom was J.J. Thompson. So J.J. Thompson, this gentleman here, in 1897, he showed that there was in fact internal structure inside atoms. And he showed through various experiments that the atom wasn't just a solid ball of featureless matter that was the same all the way through. It actually contained small negatively charged particles, which were even smaller than the atom itself, embedded somehow within that atom. So he called these particles electrons, and Thomson knew the idea, he was aware of the fact that atoms were electrically neutral overall. And so if they had negatively charged particles within them, it follows that there must be some positive charge which balances out the negative charge and makes the overall atom neutral overall. And so he argued that, yes, he said, I found experimental evidence of these tiny negatively charged particles, which he called electrons, but he also knew that the atom was neutral. And so he proposed that the atom must be made of a positively charged sphere which contains these negatively charged electrons embedded within it, like the plums in a plum pudding. And this became known as the plum pudding model. So this was the the development that of the atomic model that J.J. Thomson, this was his contribution to the development of the atomic model. And this goes beyond the simple idea that atoms are just these featureless solid balls which have the same structure all the way through, and that they have no internal parts to them. He said, yes, there are internal parts. There are these tiny, small, negatively charged electrons embedded in these solid, positively charged spheres. So along comes Ernest Rutherford. Now, he and his team of researchers in 1910, he devised a series of experiments where particles were fired, alpha particles, at a very, very thin sheet of gold film. And there was a photographic plate placed behind the sheet of gold film, which allowed him to detect what directions the alpha particles were moving in as they passed through that gold sheet. Now, what he found was that when he had his alpha particle emitter, he found that the alpha particles, they weren't all reflected, they weren't all deflected. Some of them passed all the way through, some of them were deflected at various angles, and some of them were reflected. Now, from this discovery, Rutherford proposed that the atom must have a small, very dense central nucleus where most of the matter, the mass of the atom, was concentrated, and that the electrons must be moving in orbits in the space around that nucleus. And so he extended the atomic model through this series of experiments that allowed him to reach this conclusion. Now, to illustrate this a little bit more, I'm going to make use of another one of these very useful simulations from the University of Boulder, Colorado. And again, I would thoroughly recommend any of you, particularly for physics and chemistry, going to Google and typing in PHET and then the word simulations, and this will take you to the University of Boulder, Colorado, where there are these very useful simulations that will help you understand these ideas a little bit more. So basically, this simulation gives you a diagram of on the atomic scale. So this distance here represents a distance of 6 × 10⁻⁻10 meters, very, very tiny indeed, about the scale of the average atom. These dotted lines represent the electron energy levels, and you can see here the small, dense nucleus where most of the mass of the atom is contained. So this is what Rutherford was doing. He took a gold film made up of gold particles. Now, the reason he used gold was that gold is very malleable and very dense and can be hammered into extremely thin sheets. So he fired alpha particles, represented by these, at the gold film, and he found that they were scattered. Some of them were scattered at various angles, some of them at extremely sharp angles, and some of them were deflected backwards, like this one is being. So the only way that you can really explain this is if the atoms, like Dalton was saying, were completely solid spheres, then you would imagine that all of these particles would ultimately be reflected back, and that very few of them would be bounced between the atoms to get through the gold film. The only way you can explain this is that most of the atom is in fact empty space, and the mass of the atom and also the positive charge is located in the nucleus. And this is the reason why, if we zoom into one nucleus, the nucleus, of course, is positively charged because you have lots of protons and neutrons there. The protons are all positive, the neutrons are all neutral, neither positive nor negative, and alpha particles are essentially a helium nucleus. So we have 2 protons and 2 neutrons. So you have these positively charged alpha particles, and they are being repelled by the electrostatic force of repulsion between the positive nucleus and their own positive charge. And so this explains the scattering that Rutherford observed. Now, if we compare that to the plum pudding model, then you would, if you were to fire the alpha particles through, you would make a very, very different observation here. So let's go back now to the next major development here. So in 1913, on the basis of Rutherford's theories, another scientist, a very important scientist called Niels Bohr, proposed another model of atomic structure. Now, Rutherford said that the electrons were simply whizzing around the nucleus in the space around the nucleus, but he didn't really do very much to explain anything more than that about the electrons. Niels Bohr said, yes, the electrons are moving around the nucleus, but the electrons are not just whizzing around in a random manner. In fact, the electrons behave like standing waves of energy which exist at separate, specific, discrete distances around the nucleus. Now, it was Bohr's contribution to the development of the atomic model, together with many other contributions that he made about electrons and their energy levels, which in large part was responsible for the foundations of quantum theory. So Niels Bohr is an incredibly important scientist, not just in this context, but because his work, among others, led to our understanding of quantum theory. But essentially his contribution was that the small positively charged nucleus was orbited by the electrons. Now again, he conceived of them as standing waves of energy, but it's equally useful to consider them as particles orbiting the nucleus. So for the purposes of GCSE chemistry, we can say that Niels Bohr's contribution to the our model, our understanding of atomic structure, is that particles orbit the nucleus in concentric energy levels around the nucleus. The lowest energy level being closest to the nucleus, the highest energy level being the one furthest away from the nucleus. Now, the last scientist to significantly contribute to our understanding of the atomic model is James Chadwick. Now, James Chadwick took on Rutherford's ideas and extended them further. Now, Rutherford didn't really know about neutrons, but he was aware that there was some kind of neutrality present in the nucleus. He thought of this as being pairs of electrons and protons together in the nucleus, where the electron would cancel out the charge on the proton, and that would give you one neutrally charged particle. But he didn't think of this as being one neutral particle. He thought of it as being a bound proton-electron pair in the nucleus. But in 1930, it was discovered that beryllium, the element beryllium, so I'll show you that on the periodic table here. So here is beryllium, it's a group 2 element here. It was found in 1930 that when you bombard beryllium with alpha particles, the beryllium gives off a very energetic stream of radiation. Now, it was James Chadwick's work which led to us understanding that that extremely energetic stream of radiation coming from the beryllium was in fact made up of not gamma radiation as it was first thought, but a stream of particles, each of which had the same mass as a proton, but no electrical charge at all. And so he was awarded the Nobel Prize because this was what led to essentially the discovery that the nucleus also contains particles called neutrons, which are neutral but have the same effective mass as a proton. So today, scientists accept that the atom contains a central nucleus around which the electrons orbit in different levels, and the nucleus is composed of protons and neutrons. So there are many different models used to describe the structure of an atom. Now, the term model is basically what scientists use to describe a series of ideas which are intended to explain observable and measurable phenomena. So science works by making observations about the universe and then attempting to construct models which explain those observations. And the way that it works is you make an observation, you make a hypothesis about what might be the explanation behind that. That hypothesis is a kind of tentative model that you start with. You then do experiments to confirm or refute the predictions made by that hypothesis. So if your hypothesis is correct, I make this prediction, and let's go and see if that's true by doing this experiment. If the prediction turns out to be false, it means the hypothesis is false, and therefore we can change the model and then try again. And eventually, you will make a hypothesis, a model, which consistently produces predictions which are shown to be accurate by experiment and by the accumulation of data, then you have a theory. And that theory can then be tested further by independent replication. And in this way, we refine our models of what goes on. And so this is what we've just been describing, the refinement of the atomic model by a series of scientists, each of which was adding more detail, but doing so by basing that detail on experiments that they did to extend our understanding of the existing model. So there are many different models used to describe the structure of an atom. And in this model that we're talking about, and in this animation, we can see that the electrons are orbiting around a central nucleus in these concentric energy levels or shells. But in fact, there are problems with this model because, for a start, it shows the atom as a two-dimensional object. Of course, an atom is in fact a three-dimensional object. But there are further problems with this model that we're being shown here because the nucleus is incredibly small, even in comparison to the size of the atom. And the electrons are even smaller than that. So the particle sizes being represented in this animation are nowhere near accurate in terms of scale. So in terms of scale, this is another one of those things that your exam boards need you to be aware of. And so before we go any further, then let's look a little bit at the scale of some of these particles. So I like to use this resource here that you can find on the internet at this URL. It's called The Scale of the Universe, and you can pick whatever language. I'm going to pick this, obviously. Now, the reason why this is very useful is because it shows you the scale of the very small and the very large in a very interactive way. So I'm going to fire it up, turn down the music a little bit, even though it is rather nice. So we start with a human. So the average human is 1.7 meters tall. But if we zoom in a little bit, let's see if we can zoom in and to get smaller here. So this gives you the size of a matchstick, 5 centimeters or 5 times 10 to the power minus 2 meters. Let's zoom in a bit smaller here. So a human ovum, which is about the biggest human cell, is 120 millionths of a meter, 120 micrometers, or 1.2 times 10 to the power minus 4 meters. And this is barely visible with a very sharp human eye. But if we scroll in a bit more, we get down to rather smaller cells, like the red blood cell, which is one of the smallest cells in the human body, and definitely not visible to the naked eye. We also get to parts of cells like mitochondria and chromosomes, which are even smaller still. We're still on the scale of micrometers here. So if we go further in, we get to viruses. The largest virus here is about 440 billionths of a meter, 440 nanometers, or 4.4 times 10 to the power minus 7. If we go even smaller, we get to very small viruses like the hepatitis B virus, 42 nanometers, so about 10 times smaller still. If we get even smaller, go even smaller scale, a DNA molecule is 3 nanometers wide. So that gives you 3 billionths of a meter. It's very small indeed, but we're still not down to the scale of even simple molecules like water and things like that. This is a very large molecule. So let's get a bit smaller then. So now we get to a glucose molecule. So a glucose molecule is 800 picometers, 8 times 10 to the power minus 10 meters. So incredibly small. And now we get to atoms. So a carbon atom, 340 picometers. So now picometers are extremely small, an extremely small measurement here. But let's go a little bit smaller here. So let's see if we can get down to a proton and an electron. So now we've got the hydrogen atom, the very smallest atom on the periodic table, 31 picometers. Get smaller than this, and look how far we've got to go, 10 femtometers, 10 to the power minus 10 to the power minus 12 meters. Femtometers, so we're down to femtometers, 10 to the power minus 15. Oh, we've got a bit too far here. Quarks, there we go. So here's a proton, 1 femtometer, 1 times 10 to the power minus 15 meters. So this is the scale of a proton. This is the size of a proton. Unbelievably small, unimaginably small. Now a neutron is about the same size. So we see here the relative scale, and they have the same mass as well. Proton has 1 unit of positive charge, neutron has 0 charge, neither positive nor negative. So let's see if we can get even smaller here. So the rest of these lengths are not confirmed. These are highly theoretical. But here we have up quarks and down quarks and strange quarks and charm quarks, bottom quarks, neutrinos. And so we're getting extremely small here and way beyond the kind of scale that we need to be looking at. But if we want to understand electrons, electrons are formally defined as essentially waves. So they don't appear on this diagram, but an electron has approximately 1/1800ths or 1,840th of the mass of a proton or neutron. So that gives you a sense of just how small an electron is. So I would encourage you to use this yourselves. It's actually quite interesting because you can zoom out even bigger, so you can go to the extremely large as well. And it does get quite surprising, the kinds of things that you can find when you go to the extremely large scale. So I'll let you guys have a play around with that yourselves. Okay, so how are we doing for time here? All right, so another 5 minutes and then we'll take a break. So we've covered protons, neutrons, electrons, the structures of atoms, and the development of the atomic model. Now, again, I'm going to make this PowerPoint, the slides of this PowerPoint available to you. There's an awful lot more information here. We've covered a lot of this in the discussion that we've gone to. But before we go on to the break here, let's talk about what we mean by the term isotope, because this is a very important definition here. So let me just go back and bring this over here. Alrighty. A lot of comments in the chat, but not a lot of Q&A questions posted yet. So I'm assuming that's either because I'm answering all those questions before you get to ask them, or you just don't have any questions yet. But please do, as always, if you do have any questions that arise and they're relevant questions, please do type them in the Q&A. All right, so what is an isotope then? So remember our definition of an element. Let's go back to it here. It's a substance composed of atoms, each of which has the same number of protons, the same atomic number. But atoms of the same element do exist, which are different from each other. So let's look at the periodic table here. So going back to our friend, the periodic table. So if I highlight the isotopes tabs here, so let's take hydrogen, for example. So hydrogen, all hydrogen atoms are hydrogen atoms because hydrogen uniquely has the atomic number 1. Hydrogen atoms are the only atoms which only have one proton in their nuclei. But hydrogen atoms do exist in different types. And there are actually 3 types of hydrogen atoms. They all have the atomic number 1. So here we see the atomic number 1 displayed on the bottom left-hand corner of the symbol, which is the normal way of displaying it. So we have hydrogen with a mass number of 1, hydrogen with a mass number of 2, and hydrogen with a mass number of 3. But they all have one proton. So the only difference really can be in the number of neutrons that they have. These are the isotopes of hydrogen. Now this brings us to another important point, which we're going to talk about a little bit more, particularly after the coming 5-minute break. It's the idea that there is a difference between mass number and relative atomic mass. Now, this is one of those topics that many of you, the second highest voted topic that you guys wanted me to cover in the explanatory and kind of teaching segments of this webinar. The idea of relative atomic mass seems to cause a lot of students a lot of difficulty. Now, we're going to come back to the idea of relative atomic mass in a later GCSE chemistry webinar on the subject of calculations and quantitative chemistry, where it becomes even more important. But for the moment, let's have a look here. So mass numbers are always displayed as integers, because a mass number fundamentally, and let's write ourselves a definition here, and again, I will make these whiteboard notes as well as these slides and everything else available to you on the private webinar resources page for those of you in attendance. So let's write ourselves a definition of this very important, or these 2 very important terms, and if necessary, we'll go into them in a bit more depth after the break here. So what is an isotope? What is, rapidly losing the ability to write, not very good with these graphics tablets still, so isotope. What is a mass number? We know what an atomic number is. An atomic number is the number of protons in the nucleus of an atom. So what is the distinction between the mass number and the relative atomic mass? Now, the way to think about this is mass number specifically refers to isotopes. So you can only really talk about the mass number of an isotope. And you can only really talk about the relative atomic mass of an element. So the term mass number refers to a particular isotope of a particular element. The relative atomic mass refers to a specific element. And the term isotope, again, refers to an element. So isotopes of an element. So what do these terms mean? Well, an isotope and a mass number and relative atomic mass, like many of these definitions that we've already encountered, in fact, these terms are related to each other. In order to understand one, you must understand all of these, because these terms require each other in order to define, to give definitions of them. So let's start with the isotope of an element. So isotopes are atoms of the same element with different mass numbers. And the reason for this is because they have different numbers of neutrons. So tritium, hydrogen 3, is different from deuterium, hydrogen 2, and they're both hydrogen because hydrogen has a unique atomic number, because hydrogen is an element. Okay? But they differ from each other only in the sense that these different types of atoms of hydrogen contain different numbers of neutrons in their nuclei. So isotopes of an element are atoms of the same element. In other words, they have the same atomic number, i.e., same number of neutrons, same number of protons. But atoms of the same element with different mass numbers. Now, this means, i.e., different numbers of neutrons in their nuclei. So this is the definition of an isotope. Isotopes of an element, like isotopes of hydrogen, they are atoms of the same element, hydrogen, and because they're atoms of the same element, they have the same atomic number or the same number of protons, but different numbers of neutrons. So a mass number of an isotope, because each isotope has a different mass number, is the total amount of mass in atomic mass units of an atom of that isotope. Now, as we said before, the only subatomic particles which have any kind of significant mass are protons and neutrons. So let me just go back to this. Oops, that's not where I wanted to go. Let's close that. Go back up a little bit. Here we go. All right, so to remind you, so we have protons. They have a relative charge in atomic charge units, not coulombs, but in atomic charge units. And this is relative. This is by comparison to the others. A relative charge of +1 units, a relative mass of 1 atomic mass unit. Neutrons have a relative charge of 0. They are neither positive nor negative. They have a relative mass of 1 unit. So relative mass is not measured in kilograms, the standard unit of mass. It's simply comparing the masses of these extremely small but fundamental particles which make up all atoms. So these have the same mass. But electrons have -1. Their relative charge is the same magnitude as a proton, but it's negative. But their mass is negligible. In other words, it may as well be considered to be 0, because compared to a proton or neutron, its mass is 1/1840th, that fraction of the mass of a proton or a neutron. So effectively, the mass of an electron is, to all intents and purposes, basically 0. And so basically, if you have protons and neutrons located in the nuclei of atoms, it means that most of the mass of an atom is in the nucleus. So the mass number describes the total mass, discounting the negligible mass of electrons in the nucleus of an atom of a particular isotope of an element. So let's quickly jot that down. So mass number, this is the total mass in atomic mass units, AMU, of the atom of a specific isotope of an element. Now, to all intents and purposes, i.e. id est, what this means is it's the sum of the number of protons and the number of neutrons in the nucleus of that atom of that isotope. And the reason is, if each proton has an atomic mass unit of 1 and each neutron has an atomic mass unit of 1, then if you want to know what the total mass is of atomic mass units of a particular atom of a particular isotope, you simply add up the number of protons and neutrons, and this gives you the mass number. But this is not the same as the relative atomic mass. So let's take a look again at the relative atomic mass of hydrogen. The relative atomic mass of hydrogen, as you can see here, is not an integer. It's not a whole number. So it can't be a mass number. If a mass number is a number of protons plus a number of neutrons, and these are fundamental particles, how can you have 0.008 of a neutron? You can't. In a similar way, how can you have 0.45 of a proton or a neutron in the case of chlorine? So all of these mass numbers that you're seeing here are fractional. So they can't be, or rather, all of these relative atomic masses that you're seeing here are fractional numbers, with the exception of these, which are, again, highly theoretical, and we don't really know very much about them. So there is a distinction between relative atomic mass and mass number. So let's quickly jot down what that distinction is, and then we'll go into it in a bit more depth after this coming 5-minute break. So what is the relative atomic mass then? The relative atomic mass of an element, again, this describes all of the atoms of an element, including all of the isotopes. And there's your clue. A mass number describes a particular isotope. It refers to a particular isotope, like we saw with hydrogen. Tritium has a mass number of 3, but it's still a hydrogen atom. Deuterium has a mass number of 2. It's still a hydrogen atom. And normal hydrogen, hydrogen 1, has an atomic mass number of a mass number of 1, because these are the mass numbers of particular isotopes of an element. But they're all hydrogen atoms. But the relative atomic mass of the element hydrogen describes something to do with all of the atoms of hydrogen, including all of the isotopes. So this is what a relative atomic mass is. And this is a fairly long-winded definition, but it is one that you need to memorize nonetheless. And we'll look at it again after this break in a bit more detail. So this is the weighted average of the atomic masses of the isotopes of an element. Now, the average is weighted. So it's not like a normal average. If somebody says, what is the average of the numbers 1 and 2 and 3? You simply add those 3 numbers together and divide by how many numbers you have, which is 3. That's not a weighted average. A weighted average is, let's say, for example, there are 52 of this kind of object, and there are 36 of that kind of object, and there are 54 of that kind of object, objects X, Y, and Z. And object X has a mass of 1 kilogram, object Y has a mass of 2 kilograms, and object Z has a mass of 3 kilograms. What is the weighted average of the masses of all of those objects? Now, weighted, in this case, the average of the atomic masses of the isotopes of a particular element are weighted, put in brackets, weighted according to the percentage abundance of those isotopes. But then that's still so far describes atomic mass. That the standard units of mass in science are kilograms. The problem with that is that when you're talking about kilograms, if you're looking at the mass of, say, a proton or a neutron, you're talking about masses in kilograms of, on the order of 10 to the power minus 19 of a kilogram. Incredibly small numbers, which are not very useful at all, or not particularly nice to deal with in calculations. So again, we don't use kilograms, the standard unit of mass. We use the atomic mass unit. But in this case, this number, if we just go with atomic mass, it's a mass, it would be given in kilograms. So to avoid doing that, it's compared to the mass of 1/12, or rather, let me correct that and clarify that a little bit. Compared to 1/12 of the mass of a carbon-12 atom. So whatever the mass of a carbon-12 atom is in kilograms, you divide that by 12, that gives you the actual mass of one atomic mass unit in kilograms. However many times the weighted average is bigger than that, that is the relative atomic mass of that element. So we'll look at what this means and how we calculate this after this coming 5-minute break, because I see that we've reached the end of the first hour. So I hope that was useful, guys. I see that a lot of you have seem to have had pennies drop, and you were saying, "OMG, I finally understand these definitions." So clearly, you know, it's been helpful. But like I say, if you have any actual questions, please pop those into the Q&A box. I will give you guys 5 minutes or so to have a little breather, maybe get a cup of tea or something, and I will see you in about 5 minutes' time, and we'll go into this in a bit more depth. Please, if you would like me to go straight into the exam questions, maybe type that in chat, and I will have a look at what you guys have voted for either way, whether you'd like me to continue with the teaching of this topic for the next hour or to go into the exam questions in the order in which you guys voted for them. Either way, pop that into the chat and take a break for about 5 minutes, and I will be back in about 5 minutes' time. Okay. So we're back after the 5-minute break. Let me have a look at what you guys have voted for. So let's see. Okay. So it seems like, it seems like a roughly even split. Many of you are asking for, it's about 52% exam questions, and the rest are either, almost all of the rest are to go on with the topic teaching. But in particular, even a lot of you asking for exam questions are asking for me to quickly go over the idea of isotopes and relative atomic mass before going into exam questions. Okay, so I think that's a good compromise. So how about I quickly finish off the idea of relative atomic mass, how it is calculated, and then go into the exam questions. Okay, so let's quickly go through the idea of relative atomic mass. Now, again, I'm going to use another one of these very useful simulations here, which talks about relative atomic mass in a little bit more depth here. And again, you can find these on the PHET website here. Okay, so let's quickly get into what you guys have voted for. So we'll do this, we'll finish off relative atomic mass, and then we'll get into the exam questions that you received in your exam question packs. Okay, so this simulation is quite useful because it gives you a kind of visual way of understanding what we mean by relative atomic mass. Now, if you have a look at this periodic table, if we go back to the isotopes, let's take, for example, chlorine. Now, in the periodic table, for example, in your periodic tables at GCSE level, you'll find that your periodic table often will say that the relative atomic mass of chlorine, the element, is 35.5. In fact, it's closer to 35.45 or thereabouts. But again, this illustrates the difference between relative atomic mass, which can be fractional and frequently is, and mass number. The reason for this goes back to the definition that we just talked about in the previous segment of this webinar. The relative atomic mass is the weighted average of the atomic masses of all of the isotopes of the element, and the average is weighted according to the percentage abundance of each one of those isotopes. And so the way that this is done is that different isotopes don't exist in equal amounts. So if we take, for example, the isotopes of chlorine, we find that there are actually 3 different isotopes of chlorine. They all have the atomic number of 17 because, again, as we said before, all chlorine atoms have 17 protons in their nuclei. That's what defines them as being chlorine atoms because, again, going back to those very important definitions, if we look at the definition of an element, it's a substance composed of atoms, each of which has the same number of protons, and this implies that each element of the periodic table is made up of atoms that have a unique atomic number. Hydrogen is 1, helium is 2, and as you go from left to right across the periodic table, the atomic numbers go up by 1 as you go from left to right. So each element has its own unique atomic number, as you can see here. So chlorine, all atoms of chlorine have the atomic number 17. They all have 17 protons in their nuclei. But there are 3 types of chlorine atoms, 3 isotopes of chlorine. One of them has a mass number of 35, another has a mass number of 36, another has a mass number of 37. The other thing that you need to understand about isotopes is that if an element has multiple isotopes, those isotopes of that element don't exist in equal proportions in the universe. If you went out and counted the number of chlorine atoms in a sample of chlorine that you got from a natural source, or you got it from a natural compound or something like that, you would find that you don't count an equal number of chlorine 35, chlorine 36, and chlorine 37 atoms. They exist in different abundances in nature. So we can see those abundances here. Chlorine 35 has a relative abundance of 75.78. This means that 75.78% of all chlorine atoms in general are chlorine 35, the isotope chlorine 35. Chlorine 36 exists in a relative abundance of almost 0%. So it does exist, but it's in such tiny quantities that it may as well be 0. And chlorine 37 makes up the remainder. It's about 24.22% of all chlorine atoms are chlorine 37. So these isotopes of this element do not exist in equal abundances. And the same can be said of, for example, hydrogen. So going back to hydrogen, which we looked at before, there's 3 isotopes, but they don't exist in similar abundances. Almost all hydrogen atoms in the universe with an abundance of 99.9885% are hydrogen 1, where there's just 1 proton in the nucleus, no neutrons, and so the mass number is 1. But the other 2 isotopes of hydrogen, deuterium, which has a mass number of 2, and tritium, which has a mass number of 3, they do make up that 0.0 whatever percent remainder. Yeah. So this is very, very important. Now the majority of that is deuterium with an abundance of 0.0115%, and tritium does exist, but it's in incredibly tiny quantities, even smaller than that. And so effectively, for the purposes of the accuracies being shown in this, the precision being shown in these decimal places, it's effectively 0. So these do not exist in equal quantities out in the real world. Most hydrogen atoms are just hydrogen with a mass number of 1. The remainder, almost all of the remainder, is deuterium, and with a tiny, almost negligible proportion is tritium. So this is the reason why the weighted average is weighted according to percentage abundance. So let's see how that's done. So let's bring up a calculator here so I can show you how the percentage abundance is calculated. So the way that we do weighted averages is we're trying to find, again, looking at the definition for the term isotope here. The isotope is the weighted average of the atomic masses of the isotopes weighted according to the percentage abundance of those isotopes compared to 1/12 of the mass of a carbon-12 atom. Now the reason carbon-12 was chosen, it was actually in the 1960s there was a meeting of chemists where they were trying to determine what would be the standard against which the masses of the atoms of every element would be measured. They chose carbon-12 because if we take carbon and you look at its relative atomic mass, it's almost 12, pretty much exactly. So if you divide this by 12, you get 1 atomic mass unit. So 1/12 of the mass of 1 carbon-12 atom in kilograms represents the mass in kilograms of 1 atomic mass unit. And so let's see how this is calculated. The relative atomic mass is calculated for chlorine. So going back to the isotopes then, We have 3 isotopes, but one of those isotopes is effectively in an abundance of 0. It's almost negligible. So almost all chlorine is made up of chlorine 35 or chlorine 37. So let's use this one because it's a nice visual representation. So we see here, in nature, if we were to represent them visually, about 75.76% of all chlorine atoms are chlorine 35 isotope. The remainder, almost all of them, are chlorine 37, and that's represented visually here. Now this gives us an average relative atomic mass, a weighted average. So it's weighted, so this is kind of represented as a scale, kind of a seesaw here, and it's weighted heavily in favor of chlorine 35 because chlorine 35 is much more, exists much more than chlorine 37. So how is this actually calculated though? So let's bring up our calculator. This is the way that it's done. So what you do is, you, rather than just taking 35 plus 37 and dividing by 2, which is an ordinary average, you're weighting it according to percentage abundance. So the way you do it is you take 35, which is the mass of one chlorine 35 atom in atomic mass units, you multiply it by 75.76. So that's the first part of the calculation. You add this to the mass of a chlorine 37 atom multiplied by its percentage abundance, just as we did for the chlorine 35 atom, times 24.24. And then you divide this by 100 to get the weighted average. And you get 34.48. Now this number here also takes into account the tiny proportion of atoms of chlorine 36, so it's not exactly the same, but this is how you calculate a weighted average, this is how you calculate relative atomic mass. So that's it for relative atomic mass. That's how it's calculated, that's how it's defined, and you do need to learn this definition. Like all formal definitions, you must memorize this, because you need to be able to reproduce it in case of being asked what defined the term relative atomic mass. But again, understanding how it's calculated, what we mean by a weighted average, and how it's calculated and how it's referenced against 1/12 of the mass of a carbon-12 atom, that's all encapsulated into this one definition here. Okay, so that covers what you guys wanted me to cover in terms of the subject content. Now obviously you will have access to the remaining slides of this PowerPoint, which is rather voluminous. This also includes descriptions of the development of the periodic table, and also the reactivity of various different kinds of elements in different groups, and the explanations of those in terms of their electronic structures related to their positions in the periodic table. Very few of you voted for me to cover that in the on the private webinar resources page, but again, you will have access to that page, and all of the slides of this PowerPoint will be on that page as well. And obviously you can continue to ask me questions on that page, all the way up to the end of the exam period in 2019. So please do make use of that if you do have any questions, and I'll be happy to elaborate on more of that. Okay, so let's have a crack at the exam questions then, which appeared in your exam questions pack. So let me bring this up here. All right, so now in terms of votes, the question that got the most votes in terms of the one that you all found most challenging was question 3. Let me just actually, no, sorry, it was question 2, beg your pardon. Question 2. Question 2, and then let's see here, let me just see my notes over here. Question 2, then question 4, then question 3, and then on down. Okay, so we'll cover them in that order. All right, so question 2. Dmitry Mendeleev was one of the first chemists to classify the elements by arranging them in order of their atomic weights. His periodic table was published in 1869. How did Mendeleev know that there must be undiscovered elements, and how did he take this into account when he designed his periodic table? That's the first question, part A. Part B. By the early 20th century, protons and electrons had been discovered. Describe how the knowledge of the numbers of protons and electrons in atoms allow chemists to place elements in their correct order and correct group. Part C. The transition elements are a block of elements between groups 2 and 3 of the periodic table. Transition elements have similar properties. Explain why in terms of their electronic structure. And the second part of part C, there are no transition elements between the group 2 element magnesium and the group 3 element aluminium. Give a reason why in terms of electronic structure. So that's question 2. So let's have a crack at this first. So Dmitry Mendeleev. Now, it seems like most of you had found this question tricky in terms of the wording that you're expected to use in the explanation in order to understand this. So let me bring this over here so it doesn't get in my way. Sorry, guys. All right. So in order to answer this question, I'll just use my pen here. I'll use a red pen. And again, I'll make this available to you as well as the mark scheme as well. So as I've said to you guys before in various other webinars and private sessions and things like that, you need to get into the habit of using a very rigorous, systematic approach to reading exam questions and understanding what the examiner is asking you to do before attempting to answer the question. In this case, you need to read the stem of the question. So the stem of the question is the part of the question before you see a command word appear. So the command word is not really a command word here. It's saying how did. So it's asking you to explain, essentially. It's an implicit command word here. But before, it's telling you that Mendeleev was one of the first chemists to classify the elements by arranging them in order of their atomic weights. His periodic table was published in 1869. Now, the publication of the periodic table in 1869 is pretty much irrelevant, other than to say that it's before this section of the question. But how did Mendeleev know there must be undiscovered elements, and how did he take this into account when he designed his periodic table? So there's two implicit requests for you to explain two different things, and you must do both of them to get both of these marks. So essentially, and again, another point of exam technique, which I try and hammer home to you guys again and again, is don't just pay attention to the number of marks available here. Also pay attention to the number of lines that you're being given for your answer. Now, this takes into account the number of lines that examiners have kind of discussed and also tested with focus groups of students, which would be required to give the kind of ideal answers. Not necessarily the answers as they appear in the mark scheme, but the most clear answers from the most able students. So always pay attention to the number of marks. Give yourself 1 minute per mark on average, and then pay attention to the number of lines being given to you for your answer, because these are all important clues as to how to structure your answer and the level of detail required. So essentially, the explanation for this goes into requires an understanding of the development of the periodic table. So the reason why he knew that there must be undiscovered elements was essentially Mendeleev's periodic table was based upon ordering the elements in a kind of in rows and columns, but he knew that there must be undiscovered elements essentially because if you place the elements consecutively, then the elements would have the wrong properties. They would not have properties that were similar to each other because they would appear in different groups, in different vertical columns. So to explain this, let me just quickly refer to a couple of slides from the PowerPoint, which are to do with the history of the periodic table here. So basically, before Mendeleev arrived, there was another scientist named Newland, John Newland. Now, his idea was based around a kind of philosophical idea of octaves in music. So he suggested in 1863 that the periodic table of elements, the first periodic table of elements based upon the relative atomic masses, but he organized them into octaves. So he said that every eighth element had similar properties, and this is where we get the octave from. But essentially, because it wasn't scientific, it was more of a kind of mystical and philosophical approach. He firstly was ridiculed for that, but also because he left no spaces for undiscovered elements, and also sometimes placed two elements in the same box. So along comes Mendeleev. Now this is a small part of Mendeleev's original periodic table. These are the groups as he originally stated them, and as you can see here, he left spaces where you see these asterisks for undiscovered elements. So The way that he developed this was, firstly, he organized the periodic table on the basis of physical and chemical properties of the elements. Again, this is related to physical bonding and chemical bonding as we know it today. But also, he guessed some elements were missing and he left gaps for them. Now, he published his first version of the periodic table and then used that in typical scientific fashion. As I said to you in the previous segment about the scientific method, you come up with a model, you make predictions based upon that model or hypothesis, you then do experiments and take measurements to confirm or refute the hypothesis by seeing if those predictions are proven to be accurate or erroneous or incorrect. So he left gaps for the positions of elements which he knew must have similar properties to the elements being shown in the same groups as those yet undiscovered elements. So here were his predictions about one element in particular. So he predicted that an element which was yet to be discovered would be a light grey metal, that it would form a white dioxide powder which had a high melting point, that the oxide of the element would have what he described as a specific gravity, what we would call density, of 4.7 units, and that the chloride compound of the element would boil below 100 degrees centigrade, and that the chloride would have a specific gravity of 1.9. So germanium, an element which was discovered 17 years after Mendeleev made his predictions, had the following observed properties. It's a greyish-white metal. One atom of germanium combines with 2 atoms of oxygen, therefore forming a dioxide, and the melting point of that dioxide is in fact very, very high. It's over 1,000 degrees centigrade. So again, here we see Mendeleev's prediction proving to be correct. Germanium oxide has a specific gravity, in fact, of 4.703. This is incredibly accurate based upon, or Mendeleev's prediction has proven to be incredibly accurate in this regard, as you can see. Germanium chloride, in fact, does boil below 100 degrees C. It boils at 86.5 degrees centigrade, and germanium chloride has a specific gravity of 1.887. Again, incredible accuracy shown by Mendeleev's predictions. This is an example of the scientific method being applied to the highest level here. So, as the years went by, more and more elements were discovered, and Mendeleev continued to adapt and modify his periodic table accordingly. And so as the years went by 1900, Mendeleev's table was what we would describe as version 5.0. So this is the history of Mendeleev's involvement, but it's predicated upon, firstly, organizing the elements consecutively, but leaving gaps. Otherwise, if you didn't leave those gaps, the elements would that you placed in those gaps, or rather, if you placed them consecutively, the elements would end up being in the wrong group or having the wrong properties. So that would be the first point that you would need to make in this question to get an answer here. So we can say here, if the elements were placed consecutively, they would appear sorry about that, just getting some weird errors on my other screen. They would appear in the incorrect groups Now remember, elements in the same group of the periodic table have similar properties, and therefore if the elements appear in the incorrect groups, they no longer have similar properties to each other. And if you recall, that is one of the bases on which Mendeleev organized elements into the same groups. It was the fact that some elements seem to have the same chemical and physical properties, and so he put them into the same groups, thinking that there must be some kind of order to all of this. Now, if you place them consecutively without the gaps, the elements would appear in the incorrect groups, i.e. have incorrect properties. So that would be the first thing that you could describe in your answer. Now again, I'm actually showing bad exam technique here by writing outside of the line here. So let me just correct that. So incorrect properties. Now, okay, so That's the first marking point. That would get you the first mark here. Now, how did he take this into account when he designed this periodic table? Well, this mark is much easier to define. Obviously, the implicit in this is to account for this, to account for the above, Mendeleev. Oh. Rapidly losing the ability to write. Mendeleev left gaps for undiscovered elements. And as we saw, his predictions about the properties of those undiscovered elements turned out to be remarkably correct when those elements were in fact discovered. So this would get you the 2 marks for this exam question here. So, part B. In fact, I think what's going on is that my pointer highlighter is playing merry hell with Microsoft Word, so I'm going to turn that off for the moment here. Okay, so part B. You're being asked here, first of all, the stem of this part of the question is saying that... Okay, so the stem of this part of the question, by the early 20th century, protons and electrons had been discovered, as we saw in the first segment of this webinar, where we talked about the development of the atomic model. Describe how. So here's our command word. Describe how knowledge of the numbers of protons and electrons allow chemists to place elements in their correct order and correct groups. Now, 3 marks. Now, this goes to your understanding of the arrangement of elements in the periodic table. So let's briefly review that before we address the answer to this question, just to elaborate on why the answer to this question is what it is. So going back to our friend here, the periodic table. So the modern periodic table, now this version of the periodic table, when you see it in this shape, this is not actually, believe it or not, what the periodic table really looks like. This is a way of showing the periodic table easily on one piece of paper in landscape mode while still maintaining clarity of all of these relative atomic masses and atomic numbers. The periodic table's real shape is in fact this. So let me zoom in a bit here. So this is the actual shape of the periodic table. You see here that we have the lanthanides and the actinides, these rare earth elements, in between the transition metal block, the D block, and the P block here, which contains these. We have the metals, we have the non-metals, we have the metalloids, which share properties of metals and non-metals, but in between these, we have the lanthanoids and the actinoids, and these are found between the alkaline earth metals and the post-translation metals, metalloids, and so on. So this is the real shape of the periodic table here. But let's just go back to our familiar shape where we've abbreviated it. So we see here that this term here shows you that these are in fact in between these two and these two. So the chemical and the physical properties, let's go back to our all-important definitions here. Chemical bonding is what determines chemical properties. So again, to remind you, the chemical bonding, the electrostatic forces of attraction between atoms or ions in a pure substance, an element or a compound, is what determines the chemical properties, the reactivity of those substances. But as we'll see in the next topic on bonding and structure, it's actually the the electronic structures, the structures of the shells of electrons of these elements, which determines how these elements bond. Now think about what that means for Mendeleev's periodic table. Mendeleev spent years of his life with little bits of card on which he had the symbol for one element, so he had a separate piece of card for each element, and on the back of that piece of card he had a description of the known physical and chemical properties of that element. And he just shuffled those bits of card around on a big table until he could organize elements with similar chemical and physical properties into groups with each other. And therefore, before we knew anything about electrons, elements were organized into vertical columns, groups, because they share similar chemical properties. But those chemical properties are determined by the type of chemical bonding in them. And the chemical bonding in turn is bonding between atoms or ions, as we see here, and that in turn is dependent upon electrons. So what are we really saying here? What we're saying is the chemical properties are dependent ultimately on the electronic structure, the way in which electrons are arranged in those atoms of those elements. And so what we can say is, if the elements in a particular group, like group 1, share similar chemical properties with each other, it's because the atoms of those elements have similar electronic structures. Specifically, the atoms have the same number of electrons in the highest occupied energy level, the outermost shell of the atom. And this is why they bond in a similar way chemically and therefore have similar chemical properties. Similarly, the atoms in group 7, which actually is group 17, but that's another story. For the purposes of GCSE students, this is group 7. The atoms in group 7 share similar chemical properties because they have similar chemical bonding or they bond in a similar manner with other atoms. But that in turn is determined by the similarity in their electronic structure, in the arrangement of electrons in those atoms. Specifically, all of the atoms in group 7 have 7 electrons in their outermost shells. So the vertical column, the group numbers, group 1, group 2, and as far as you guys are concerned, group 3, group 4, group 5, group 6, group 7, group 0, this tells you from groups 1 to 7, the number of electrons in the outermost shells of the atoms, the unbonded atoms of those elements. So, in terms of properties, similar properties in the same group because they have the same number of electrons in the outer shells of their atoms. But now let's look at the period number. It's called the periodic table because they're all organized into horizontal rows or periods. Now, the period also tells you something about the organization of electrons in the outer shells of the atoms. As you go from left to right, the atomic number is increasing. So if we take the second period, we have lithium, which has the atomic number 3, beryllium is 4, boron is 5, carbon is 6, nitrogen 7, and so on. This tells us, as we go from left to right, the atoms of these elements have 1 extra proton from one to the other. But this also tells you they have 1 extra electron, which in turn implies that the electronic structure is changing but similar. The period number tells you the total number of energy levels of electrons in those atoms. In hydrogen and helium, there is only 1 shell of electrons. In hydrogen, that first shell has 1 electron. In helium, that first shell has 2 electrons. In the elements of the second short period, the second period here, the second horizontal row, all of these elements, the atoms of those elements only have 2 electron shells. All of the atoms of the elements in period 3 have 3 shells of electrons, the third one being the outer shell. All of the atoms of the elements in period 4 have 4 shells of electrons, and so on. So the original arrangement of elements in the periodic table was on the basis of their similar chemical and physical properties. But later on, those chemical and physical properties were found to be fundamentally based upon the chemical and physical bonding, which in turn are based upon the electron arrangements in the atoms of those elements. And so it was found that the reason the atoms in the group in the same group have similar chemical properties is because they share similar outer shell structures. They have the same number of electrons in their outermost shell, whichever that outermost shell happens to be. The atoms in the same period have also similar shells, similar electron arrangements in the sense that they have similar numbers of electrons in their similar numbers of shells of electrons. All of the elements in period 1 have 1 shell of electrons. All of the elements in period 2, the atoms have 2 shells, 3 shells, 4 shells, 5 shells, and so on. So going back to our question then, how does the knowledge of number of protons and electrons, so when you're answering exam questions, you must give the examiner everything they want. You can't just talk about protons here. You must talk about number of protons and electrons, numbers of them, and how it relates to placing elements in their correct order and correct group. So notice the wording being used here. Yeah, this is how you need to pick apart an exam question before you start to answer them. Now, obviously, I'm belaboring the point somewhat because I'm explaining all of the kind of knowledge behind it. But once you've internalized that knowledge, you should be spending a bit of time with each exam question, just trying to really get to grips with the details of exactly what the examiner is asking you to do. So again, in general, you should pay attention to the number of marks, give yourself that many minutes to answer, and also pay attention to the number of lines that you're being given in order to give the best answer possible. This gives you a framework gives you a hint as to how to organize your answer and the level of detail and amount of words that maybe the examiner is expecting from you. Okay, so with all of that in mind, let's now answer this question then. So, first of all, as we've said, elements are placed in order of atomic number, or the number of protons going from left to right. So, elements are organized in order of increasing atomic or proton number going from left to right. So that statement alone, because you've described how the elements are being placed in order in terms of protons, that gets you the first mark. Now, elements in the this is describing the horizontal arrangement in how the elements are organized in each period. The second mark is for saying that elements in the same group Now, again, we're using the proper terms here. Don't say vertical column when there is a specific chemical term to describe that group. So elements in the same group have the same number of outermost electrons. So the same number of electrons in outermost shell. I'm using the term shell here in inverted commas because, strictly speaking, it's the highest occupied energy level, but for GCSE level this is fine. So this would get you the second mark of the 3 marks available. Now, there's a number of different ways you can score the third mark, all of which are equally valid. So it's asked, so far we've talked about electrons in terms of the shells, the arrangement of shells. We've talked about the number of protons, but describe how knowledge of the numbers of protons and electrons place elements in the correct order and the correct group. So simply saying these two things, if we're going by the 1 mark per logical point guideline, will not get you all 3 marks. There must be something else which you need to say here. Now again, think about how the elements were organized originally before we knew anything about protons or electrons. Well, they were organized by Mendeleev in terms of their physical and their chemical properties. Physical properties are based upon physical bonding, but chemical properties, the chemical reactivity, is based upon chemical bonding. And chemical bonding, as you should know, and as we'll see in the next GCSE Chemistry webinar, is based upon the electronic structures of the atoms of those elements. So we can link these together to the original arrangement of elements in the periodic table by saying that the chemical properties, or the reactivity, chemical properties, reactivities of elements in the same group. Again, use the term group, don't say vertical column. In the same group are similar because they have the same number of electrons in their outermost shells. So that would get you the third mark. But again, there are other things that you could say. You could simply say for that third mark that there are an equal number of protons to electrons in an atom. You're still forming a link between these two concepts, which is again what the examiner is asking for here. You could, for example, also say that going back to the point that I made about the period number tells you the number of shells. Now, again, we haven't gone into the explanation of reactivity of different elements, but it is fairly simple. Group 1 and Group 2 metals achieve stability, the atoms achieve stability by giving up their outermost electrons. Group 6 and 7 elements will achieve stability by filling the outermost shell by gaining 2 or 1 electrons respectively. And so the ease with which these atoms can give up their outer electrons will determine how easily or how readily they will react. It will determine their reactivity. And so as you go down Group 1, the outermost electrons become further and further away from the nucleus, which is holding them by electrostatic attraction to the atom, and therefore they will be lost more easily. And so as you go down Group 1 and also down Group 2, you get more and more reactive metals. With Group 6 and 7, these atoms will react by gaining electrons from other atoms, and so obviously the more powerfully they can attract those electrons into their outermost shells, the more readily they will react, the more readily and vigorously they will gain electrons from other atoms. And so as you go down these groups, the outermost shell is further away from that positive nucleus, which is doing the attracting of those negative electrons, and therefore they are less reactive for that reason. And so you could simply say for the third mark instead that the reactivity is based upon the period structure as well, and the period determines the number of electron shells there are between the nucleus and the outermost shell. But anyway, that gives you an idea of how to get those 3 marks. Okay, part C. The transition elements are a block of elements between Group 2 and 3 of the periodic table. Again, this goes back to the actual proper shape of the periodic table that I just showed you. And the transition elements have similar properties. Now, explain why in terms of electronic structure. Now, this actually is a pretty tricky question because not many GCSE exam questions will ask you about electronic structure of transition elements. Now, the proper way to answer this, now this goes to the reason why some of you probably are wondering, and some of you have asked in the chat box, why do these groups have numbers in this periodic table? Well, because actually when you study chemistry to a higher level, you realize that this is actually Group 13, not Group 3. This is Group 14, not Group 4. It's because the transition elements actually do have group numbers. But they are called the D block for a reason. It's because the shells of electrons that you're taught about at GCSE is a simplification. In fact, those shells are divided into subshells. So in fact, these are the shapes of the electron shells. As you can see here, these dumbbell shapes and even weirder and wackier and wonderful shapes that you can see here. Now, the D block elements have similar electronic structures, which is why they're called the D block elements. You have subshells called S subshells, P subshells, D subshells, and F subshells. So let's decomplexify this and give it in terms of GCSE language now. So to answer this question, again, think about what I've been saying to you about chemical properties being based upon chemical bonding. Chemical bonding are bonds between atoms or ions, and again, thinking about what you know about bonding between atoms and ions, you should know that chemical bonds, ionic bonds, covalent bonds, metallic bonds, these occur by transferring or sharing electrons from the outermost shells of atoms. Therefore, if you have similar outer shell structures, you must have similar chemical bonding and therefore similar chemical properties. And so, to answer this question, you can say that in terms of electronic structure, and again, this is a simplification, but usually transition metal elements have similar fourth shell structures or similar numbers, I guess, similar numbers of fourth shell electrons So that would be the first point. And the reason they have similar numbers of fourth shell electrons is because the third shell is already filled. Now again, this is somewhat of a simplification, but this will get you the 2 marks for this question. Okay, now, second part of part C of this question, there are no transition elements between the group 2 element magnesium and the group 3 element aluminium. So let's have a look at our periodic table just to illustrate that. So magnesium all the way to aluminium, there are no transition elements between these two elements here. We go straight from atomic number 12 to atomic number 13 with nothing in between. Give a reason why in terms of their electronic structure. Well, this is actually a comparatively easy question to answer, but you do need to kind of answer it clearly to get this 1 mark. And you'll notice that you're being given 3 lines here to make this answer for a 1 mark question, which is relatively uncommon at GCSE. Normally it will be 1, maximum 2 lines. So always pay attention to the number of lines that you're being given, not just the number of marks. A 1 mark answer isn't necessarily any more in the new specifications a single word or a couple of words. It may be a sentence. It may even be a short paragraph. So be very careful to pay attention to the number of lines here. So give a reason why in terms of electronic structure. So when you see this phrase in terms of, it means give your answer using these ideas as an explanation or as part of your explanation. So no transition elements between group 2 element magnesium and the group 3 element aluminium. Give your answer in terms of electronic structure. Well, let's have a look at the electronic structures of these 2 elements. Magnesium is atomic number 12, aluminium is atomic number 13. Now, if you want to formulate the electronic structures of elements like these, what you need to do, a very simple way of doing it, is again, look at the group number, look at the period number. Group number tells you the number of electrons in the outermost shell. Period number tells you the number of shells. So if there are 3 shells, obviously the third shell must be the outermost shell, and they're both in the third period, so they both must have 3 shells. So let's start with that as our idea here. So again, anything that you're doing as a working out that you don't necessarily need to include in the final answer, you can do in the space around the question here. So we have magnesium, we have aluminium. Magnesium, it has 3 shells, which I'm going to draw rather messily with my rubbish drawing skills, but it should be reasonably clear anyway. So 3 shells. They're both in period 3, they both have 3 shells. Magnesium is in group 2. Group number tells you the number of electrons in the outermost shell. Outermost shell is the third shell, therefore there's 2 electrons here. Aluminium is in group 3. Group number tells you the number of electrons in the outermost shell, so there are 3 electrons in this one. Now, this implies that all of the underlying shells must already be filled, and as you know, the rules are as follows: 2, 8. 18 is the actual number of electrons in the third shell, but for GCSE purposes, you can just use 8. And then anything else goes in the fourth shell. And you'll never be asked to draw an electron configuration or diagram or notation for anything that has anything more than a couple of electrons in the fourth shell. So magnesium must have 2 in the innermost because it must be filled already, and 8 in the second because the second shell must already be filled if the third shell is the outermost shell. And aluminium similarly must have 2 in the innermost because it must be filled, and 8 in the next because that one must be filled also because the third shell is the outermost shell. So magnesium has the electron configuration 2, 8, 2. Aluminium has the electron configuration 2, 8, 3. Now what this tells us, they must be in this, there are no transition elements because you go from one electron configuration straight to the next one. So the second energy level can only have a maximum of 8 electrons, and therefore any further electrons must go in the third energy level. And if you're going from 2 electrons in the third energy level to 3 electrons in the third energy level, there can be no elements in between. That's the reason. So we can say that second shell is fully occupied. Well, not if. Is fully occupied. Therefore, if magnesium atomic number is 12 and aluminium's is 13, they must both have electrons, or must both have rather, must both have outermost electrons so 2 in the case of magnesium and 3 respectively in the case of aluminium in the third shell. So this is the explanation. There can be no elements in between because you're going straight from a second electron in the third shell to a third electron in the third shell. So there's your answer. And as you can see, that's actually quite a long-winded answer for a 1-mark question. But specifications have changed since last year. They are more rigorous. They require more detail from you as the student, even to get a 1-mark answer. Now, admittedly, I have selected some of the more challenging questions to put into these exam question packs, but after all, you're not going to challenge yourself unless you challenge yourself against tougher questions. Okay guys, so it seems like we've come to the end of the second hour of this webinar, so I will give you another 5-minute break. What I'd like you to do, please, is to vote, as always, as to whether you would like me to extend this webinar by another half hour before going into the Q&A session, or if you'd like me to go straight into the half-hour Q&A session. There's not that many questions actually that have been asked, so this might be a little bit of a shorter webinar if you choose for me to go straight into the Q&A. But again, I'll give you a 5-minute break and you guys can decide for yourselves. So think about whether you'd like me to continue for half an hour. If you would like me to continue for an extra half hour, could you also please let me know by voting as to whether you'd like me to continue with a particular aspect of the topic teaching, or whether you'd like me to continue to go on to the second highest voted question from the exam question pack, which I believe was question 4. And then I think the next one was question 3. So we'll go through those in order, or whether you'd like me to continue for half an hour and go into the topic teaching. Now, the next most highest voted topic that you concept within this topic that you will find particularly difficult was the reactivities of the group 1 and 2 and 7 and group 7 elements. We have kind of covered that, but if you'd like me to go into those, I can do that as well. So I'll give you a 5-minute break. Please cast your votes in either the on-screen voting, which should appear on your screen. If you don't see that, then just let me know whether you'd like me to continue for an extra half hour, and if so, for what, or whether you'd like us to go into the Q&A in the chat box, and I will see you in about 5 minutes time. Okay, everyone, we're back after the second 5-minute break. All right, so let's have a look at what you guys voted for. So, let's see. Okay, it seems like about 80-20 between, so it seems like most of you have voted for me to go straight into the Q&A. That's fine. Don't forget, please, that I will be uploading the mark schemes for all of these questions. And again, if you have any further questions about any of these, once you've seen the mark schemes, if you're ambiguous about anything, or if you want me to elaborate on any of these, then please do type those questions that you have, or any requests for further information into the into either the chat or as a private message to me on the private webinar resources page that you will have access to. And again, to remind you, if you want the link for that, just go to your exam questions pack and click the link on the first page that you see here. This link that you see here, that will take you to the private resources page. I'll click that there just to bring it up on the screen for you, just to show you that link. And again, all of the oops, sorry about that, it's a bit deafening. But again, you will have access to the chat and also the private resources page in general. All of the resources will be uploaded here within about 48 hours. You can either send me a private message by typing in your private message here, the question, click this, check this box here, and then click the button. That will send me a private message. But if you'd like to get a discussion going, and also I will respond to messages here, you can type your questions in here and then post the comment, and I will get back to you, again, usually within 24 to 48 hours. Alrighty, so let's have a look at the Q&A box here. So quite a few questions from 2 of the 4 schools and no questions from our private students. All right, so interesting question here. Do the group 0 elements form any compounds at all with the other elements? Well, yes, I alluded to this in the first part. One of the compounds that I gave as an example of a compound here is xenon tetrafluoride. Xenon, of course, is a group 0 or element, or a noble gas. We see here. Let me just increase this in size so you can see it a bit more clearly. So xenon is a noble gas. It is very unreactive as a result, but under extreme conditions you can get it to react. Now, if you wanted to get it to react, the element, logically, if xenon itself is very unreactive, you would want to pick a highly reactive element to react it with. Now, pretty much the most chemically reactive element that you can get hold of in the periodic table is fluorine. Fluorine is nasty, nasty stuff. It's so reactive that if you take fluorine gas and just, let's say you had a lump of iron, and iron is not a particularly reactive metal, it's relatively low on the reactivity series. If you take a lump of iron and you blow fluorine gas past it, it will react with the iron, and it will actually combust. You will see the iron burning in the fluorine gas to produce iron fluoride. So that gives you a sense of just how reactive fluorine is. Now, xenon tetrafluoride is a molecule, is a compound composed of molecules, each of which contains 1 atom of xenon and 1 atom of fluorine. So let me just bring up my 3D molecular modeling application here. So I'll show you what a molecule of xenon tetrafluoride looks like. Tetrafluoride. So this would be a ball and stick diagram of xenon tetrafluoride. We can see here we have 1 xenon atom in the center, and it's bonded covalently to 4 fluorine atoms. So this would be the structural formula of xenon tetrafluoride. This would be a ball and stick model. Now, ball and stick models, they are models. They show you the relative angles of the bonds between the atoms, and it also shows you the relative sizes of those atoms. So we can see here the xenon atom is relatively large in comparison to the fluorine atom, and that's what you would expect if you take a look at the position of xenon down here in the 5th period versus fluorine, which is in the 2nd period. So fluorine only has 2 shells of electrons, the outermost being the 2nd. Xenon has 5. So again, that's why you would expect to see a larger xenon atom than a fluorine atom. But in fact, this is not the only kind of 3-dimensional molecular model that we can look at. There are so-called space-filling models as well, which actually show you a little bit more accurately what the molecule would look like. So let me just switch to one of those. Space filling. Here we go. So this is a molecule of xenon tetrafluoride. So this would be the xenon, central xenon atom. As you can see here, you've got the 4 fluorine atoms. So this outer surface represents the outermost electron energy levels of the 5 atoms that make up this molecule. So xenon tetrafluoride is a compound of a group 0 element, and as you can see, they do form compounds, but it's typically only with the most reactive elements of the periodic table, things like fluorine. So good question there. Another question. Let's have a look here, see which ones have been upvoted. There's only a few actually. Okay, so another question was, can I go into an explanation of the trend of reactivity of the group 1, or rather the trends in physical properties of the group 1 elements? Good. So yes, so we've talked an awful lot about chemical properties. We also need to talk a little bit about the physical properties. Now again, remember, physical properties are called physical properties. They're characteristics of the material, properties, but which relate to physical processes, which can be measured or observed in physical changes and physical processes. So we're talking about melting point, boiling point, density, electrical conductivity, thermal conductivity. These are all properties which relate to physical processes which they're called physical because they don't involve chemical changes. Chemical changes are when the chemical formulae of substances change due to chemical bonds between atoms. So you see how important these definitions are, because they're all interrelated. So physical properties, like the ones that I've described, will show a trend as you go down a group, within a group, or they will show trends as you go across the periodic table, across periods. So let me quickly bring up some slides to illustrate that. So let's find those. Let's see here. Sorry guys, I'm just quickly going down. Alrighty, so alkali metals. So alkali metals, we've talked a little bit about them. These are lumps of sodium. Sodium is kept, like most of the group 1, like all of the group 1 metals, it's kept under oil to prevent the surface of the sodium from oxidizing by reacting with oxygen in the atmosphere. So when you take one of these pieces of very soft metal and you cut it, it is very soft. There is a physical property. So softness, or rather the hardness, is a physical property. Now this is a metal, remember. Metals are, and it's also an element. So all of the atoms in this piece of matter are sodium atoms, and because they are all metal atoms, they bond with each other by a type of chemical bonding called metallic bonding. Now again, bonding and structure is something that we're going to get into in the next GCSE Chemistry webinar, I should say. Sorry, a bit of a brain freeze there. But just to give you a basic idea of what we're talking about, so in a metal, all of the atoms of the metal have become ions. Again, this goes back, once again, you'll be probably not surprised at this point to hear, this goes back again to one of our definitions here. An ion is an atom which has lost or gained an electron. So particles can be described as being atoms, ions, or molecules. Ions are atoms or molecules which have gained a net positive or negative charge because they've either lost or gained electrons. So when you take lots of sodium atoms, which are all neutral, you put them all together in a elemental sodium element. Each one of those sodium atoms shares its outermost electron with all the other sodium atoms, and those outermost electrons become delocalized. They are not localized to any particular atom. They are able to move freely between those metal ions, and then those negatively charged electrons, those delocalized electrons, act as a negatively charged glue which hold all of the positively charged metal ions in that lump of metal together, because of course each of these atoms has now lost an electron into this sea of delocalized electrons, and so it's become a singly positively charged, a unipositive ion. But the electrons are negatively charged, and so the electrons attract the positive ions. The positive ions attract the electrons, and so all these positive ions are held in place, they're all stuck together by this negatively charged glue of electrons, of delocalized electrons in between them. Now, if you have a group 1 metal where you have relatively small atoms with a single positive charge on them, with negative charges between them, the strength of attraction, electrostatic forces between the metal ions and the electrons is going to be relatively weak, and therefore the forces holding together that lump of metal are going to be relatively weak, and therefore the metal is going to be relatively soft. And so here we can see the reason why the Group 1 metals are relatively soft in general. It's because the metallic bonding is relatively weak, because the electrostatic forces between the positive ions and the negatively charged electrons are relatively weak, because each positive ion only has a single positive charge. If we take, in contrast to that, if we look at the, let's say, Group 2 elements, the Group 2 elements typically are harder metals than these Group 1 elements. They're still somewhat soft, but they are definitely harder than these, than the Group 1 elements. And the reason is that rather than having a single positive charge, each one of those ions has 2 positive charges, because it's given up 2 electrons into the delocalized electron C in between the positive ions. And so the attractive force holding together that metal, the metallic bonding, is stronger in a Group 2 element than in a Group 1 element. However, as you go down the group, they become softer and softer and softer, because the ions become larger, so that single positive charge is dispersed over a larger ion, and so the charge density is less, and so the attractive forces are less. So here we can see one of the trends in the physical properties of these metallic ions. So let's have a look at some of the other physical properties, the melting and the boiling points in particular. Now, when you melt or boil something, what you're doing is you're providing thermal energy to the particles so that they can vibrate fast enough to overcome the forces keeping them together to become either a liquid or a gas. And therefore, the stronger the bonding, the higher the temperature at which that will happen. The weaker the bonding, the lower the temperature at which that will happen. So both the melting and the boiling points of the Group 1 metals, the alkali metals, will decrease as you go down the group. And this is because the forces that hold the atoms together are weaker in larger atoms or ions in the metallic bonding structure. These get weaker as you go down the group, and therefore, if you look at the metals, lithium, sodium, and so on, down the group, down Group 1, you'll see that the melting points and the boiling points are decreasing as you go down the group. This is because the metal ions in that metallically bonded structure are larger, and so the electrostatic forces are weaker. So there we can see one of the physical properties. Now, density. They all have low densities, they all float on water, but the density increases as you go down the group. Now, the only anomaly in that trend is potassium. So lithium, density of 0.54 grams per centimeter cubed. Sodium is more dense. The only anomaly here is potassium, which decreases slightly, and then the trend continues. So heat and electrical conductivity. Now, the alkali metals, they are all metals. Metals will all conduct heat and electricity reasonably well. So if we take, for example, 2 electrodes, and we have a power supply and a bulb, and we sink one of those electrodes into a lump of sodium, we will complete the circuit. Now, the reason for this, again, goes back to this model here. Now, I covered this in yesterday's GCSE physics webinar on electricity, but again, it bears repeating here because it is relevant. This is how the electrons move when you just have a lump of metal with no potential difference across it. If you connect a potential difference like a power supply across this, then you have an electric current, which is where all of the electrons, the delocalized electrons, move in the same average direction through the conductor, and this is what transfers the electrical energy around the circuit. Now, in a similar this is a similar reason why metals tend to have both a high electrical conductivity as well as a high thermal conductivity. The delocalized electrons are very good at not just transferring electrical energy, but also thermal energy. When you heat one end of the metal, the heat energy is passed on not just by the vibrations of the metal ions, but also by the delocalized electrons, which will transfer that energy along. So that kind of gets into some of the physical properties of the group 1 metals and how the trends in those change down the group. Let's see if we've got some other questions here. There's a lot of people asking me, yes, all of a sudden a lot of questions popping up from a couple of the schools asking me to draw some more molecular models. Is there anything in particular you'd like me to draw a molecular model of? It seems to be the last question here. How about we look at the distinction between atoms and molecules here? Because again, this is more to do with the next the next topic, but we'll finish off on this just for a bit of fun here, because a lot of you seem to quite like the molecular modelling here. Okay, so let's bring this back up here and start a new document. Okay, so I mentioned that there is a distinction between atoms and molecules. So atoms are just the smallest particles that constitute an element. When they bond together, they form molecules. In particular, the term molecule is most properly used to describe groups of atoms covalently bonded together. So if we take, for example, we've already seen one covalently bonded molecule, xenon tetrafluoride. Let's have a look at the shapes of some other molecules, and then we'll finish off on that, because that kind of leads us nicely into the next webinar topic for GCSE Chemistry, which we'll be covering next time. So let's have a look at water. So water is H2O. It is a bent molecule. It has this V shape. And part of the reason for that is because the oxygen atom here shares one of its 6 outer electrons with this hydrogen. It shares another one of those 6 outer electrons with this hydrogen. But what you're not seeing here in this ball and stick model is at this location and at this location, you have 2 pairs of non-bonding electrons which repel these bonding pairs and turn it into this V shape. So this is the shape of a water molecule. Now if we compare this, so if we have a look at, for example, nitrogen. Now again, just to remind you, nitrogen is right next to oxygen. It's in what you guys probably call group 5 versus group 6 for oxygen. So if we have a look at how nitrogen bonds with hydrogen, and that would be NH3 or ammonia. So now we can see these 2 molecules here. Let's zoom in on the nitrogen a little bit, or the ammonia a little bit. So ammonia has a pyramidal shape. Now again, the shape of this molecule is is because it has this shape because nitrogen, if you look at the position of nitrogen in the periodic table, it's in group 5, which means it has 6 electrons in the outer shell of this nitrogen atom, and each one of these hydrogens can only form a single covalent bond sharing 1 electron with this. So there's 2 pairs of shared electrons here, one from the nitrogen here, one from the nitrogen here, one from the nitrogen here. That leaves a pair of non-bonding electrons to complete the outer shell of the nitrogen atom. Now the non-bonding pair repels these bonding pairs to the point where this molecule becomes this triangular-based pyramidal shape here. Now if we compare this to the water molecule has this bent structure. So you can see that the shapes of the oxides of a group 5 element versus a group 6 element are different. And again, this is to do with the outer shell structure. So if we take a group 4 element like carbon, so carbon, when you make CH4 with it, you're making methane. So methane. Let's finish off with this one. So methane looks like this. Let's zoom in on this. Bring it over here. And then rotate it. All right, so methane, as you can see, is this shape. This is a shape that we refer to as tetrahedral, because if you join the corners of this shape here, you form a 4-sided shape with triangular sides, a tetrahedron. Now the reason for this is because there are no non-bonding electrons in the outer shell of this carbon atom. You have carbon, which is in group 4, again, to remind you, there's carbon in what you call group 4, 4 electrons in its outermost shell. Hydrogen, being in group 1, can only form 1 covalent bond with each of those outer shell electrons, so each carbon can bond to a maximum of 4 hydrogen atoms, and so methane is CH4. So each one of the carbon's outer shell electrons is locked up in each one of these 4 bonds. There are no non-bonding electrons, and so we have the tetrahedral shape of the carbon atom compared with the shape of the group 5 hydride, ammonia, NH3, versus the compound with hydrogen of the group 6 element. But we'll get into that in the next webinar, which is going to be on structure and bonding. All right, guys, so I guess that's it. There's no other relevant questions here, so I hope that was useful to all of you. I will upload the whiteboard notes, the mark scheme for the exam questions, and also obviously the interactive version of this video with the embedded questions, and the slides from the PowerPoint to your private webinar resources page. As always, if you have any questions, please type those either in the live chat on that page for those of you who are attendees, or you can send me a private message through the private webinar resources page as well. To those of you watching this as a recording elsewhere, unfortunately, obviously you will not have access to those resources, but hopefully this video will be useful to your revision anyway. Good luck in your revision, and I will see you in the next one. Take care.